recording. All right? Okay. All right. Now, notice the good. Tammy's like, what the hell is that? Good. Don't worry. We're going to talk about that right now. Press grab. Now, I like what I hear. Stop. That's good. What you don't see, but we're going to explore right now, is what happens to it when it does. How does it fit right here?
Great.
Holy crap! It's gorgeous. But what's going on in here? How well is it doing there? Let's go take a look. What I want you to do is I want you to zoom in on that area. Okay. So the way you do that. Anybody ever? Do we talk about Z-box in here?
Nope.
Okay. This is a fun little trick your TI can do. It's very, very handy. So you press zoom. Select Z-box. 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 So grab Z-box. What you're going to do is you're going to draw a box around what you want to zoom in on. So essentially, we want to draw a box right around this area down here. Now here's the unfortunate part. You have to scroll down there. So you have to use your arrow keys. See that little target right there? You got to kind of get him close to where you want to start a corner of your box. I put him like right about there. That's kind of like, if you will, it's above and left of what I want to zoom in on. Does that make sense? Okay, so put it there, or ish there. I mean, you don't have to be in the exact same place I am. Press enter one time, and just one time. That little box changes to a blinky box now. Now drag your cursor so it's down here. And what you'll see is as you do that, I know it's thrilling. A box opens up. That's okay. It's thrilling, I know. A box opens up around that region. Aha. Yes, aha. No. So we just done right there. You've drawn a box around that. When you press enter a second time, what it will do is it will stretch that into the visible window. So this corner will get stretched up to there, this one up to there, this one down to there, and this one down to there. And it's going to blow up that region. Essentially the same as on your iPhone, if you could do this with your iPhone. Doing that and zooming in. So press enter again. Boom! Look! Look! Ah! Remember we couldn't see that? Remember we couldn't see that in the big view? But now it's there, and look what it's doing. It's coming in real damn close. Remember how these data points looked like they were on the axis in that big view? They're not on the axis. You know that. They're above the axis. They have positive values. But now, but now you can zoom in. Now you can zoom in and look what the tail's doing. Or I should say, what's the tail not doing? It's not rocketing up or rocketing down. It looks like it's kind of laying down along this axis. But I'm not sure because it's still above it. So maybe what we should do, let's fuck with the window first. Here's what I want you to do first. Press the window button. You see how the X max tops out at 9.3? Well, that makes perfect sense because our biggest X was 9. Make it go out to like 20. Which some of you are going to say, that's dumb. I was like, that's okay, you can say it's dumb. If you're thinking that. It's totally fine if it is. Because we didn't have any that high, right? But eventually, wouldn't somebody take 20 flips to get heads? It would happen. Maybe. At some point, no, it would have to predictably. Probability, this is what we're going into in 2 weeks. The basis of probability says it has to happen somewhere. It just didn't happen to us. We didn't have enough trials to do it. There's a reason for that, probabilistic reason. So press graph, what you'll see. Now notice what happens. And then magically the damn curve just disappears. It's coming down, that's what we were just looking at, yes? And then it's just like, oh, where'd it go? Z-box. Z-box, yes. Z-box. I said, did it really disappear? Well, I don't know, let's take a look. I'm going to back up so I get a data point too. Oh. Wait. Oh, my French speaking student left, that's a shame. Speaking really French up here. Oh. Look! Look!
Where?
There! And look, it disappears again! But did it disappear?
No.
What? So why can we, if you can keep Z-boxing, and do you notice something? Do you notice something as you keep Z-boxing in? Number one, it's getting closer and closer to that horizontal line. And do you notice how this shape always looks the same? No matter how close in we zoom, it always looks exactly the same. Has anybody ever heard of something called a fractal? A fractal? Self-similarity? A fractal. So the idea is, I'll give you a non-math example. Have you ever climbed a mountain? Or gone up a large rocky hillside or something like that? The argument, there we go, or fallen down one. So the idea is when you look at those hillsides, they have a certain shape to them, right? The argument is, the fractal argument is, if you get down into that hillside and look at the components that make up the hillside, the individual components have a similar shape to the overriding hillside. The rocks on a mountain look kind of like little tiny mountains. And the component structures of the rocks on the mountain that look like the mountain look like the rock that looks like the mountain. So self-similarity. As you get a finer and finer look at those items, each shape looks like the shape larger than it, much like what's going on right here. Let's do it one more time to drive the point home. Zoom in on, you might all have different windows than me right now, but I guarantee we're all getting similar shaped curves, aren't we? Yeah, we are. So let's zoom in again. Let's zoom in again. We're going to do one more. There's our last data point. There's your 9-1. Was that Rodolfo? 9-1 or was that Pete? I can't remember. 9-1. There you are. We're gonna bid you adieu. That's what I'm saying, you know? We? Adieu? No, not really. No. Look! It's friggin' awesome. That's totally friggin' awesome. Is it ever gonna touch?
Nope.
Why?
Because it's exponential.
Well, that's a good answer. Explain it. So Randall's got a vote. It's never going to touch the horizontal axis. And his vote is it can never touch, and I said, why? And he said, because it's exponential. That's a good answer. But why does it being exponential mean it's never going to touch? What I want to do is, I want to go back to the equation now. Because that's the graph of an equation, correct? That's the graph of an equation, yes? And the equation we found is sitting there in y1. So what I'm going to do is I'm going to write that equation on the board. I'm going to round it down to a sensible number of decimals, if that's okay with you guys, because it's kind of obnoxious looking right now. So the equation that you guys just found, which is a gorgeous fit. There we go. We won't get to the cards till Monday. Is that okay with you guys? I apologize. I'll have a quiz up for next week that you'll model this with your TIs rolling a die, but you'll use your TIs to roll a die for you. So same exact kind of project. So coin equation.
What was that?
Y equals 267-ish times, see that times right there? All this, you can ignore all this stuff. That's just precision we're not allowed to have, if you will. We don't have that precision. Times 0.5, I'm going to call that 0.53, because we got a lot of precision here we're not allowed to either. 0.53. And then you see this very important bit at the end here, which is very easy to ignore. That's what makes it exponential. Times 0.53 to the x power. And that looks vastly different than any parabola or line or cubic or anything. Because in all of those that we've been looking at, there's a point there, I apologize. In all those ones we were just looking at, linear, quadratic, cubic, quartic, it was always x to a number, x squared, x cubed, x to the fourth. What's happened is it's been switched now. Instead of the variable being here and the number being here, the number's here and the variable's here. So this goes back to what Carrie was saying about what happens when you vary the exponent. So how does that explain that it can never ever hit the x-axis? From a math perspective, why can that never hit the x-axis? Oh, Carrie's I'm processing. You're processing. Good for you, sister. Brittany.
Something about raising to the power of 0.
Well, can I ask it a different way?
Yeah.
Let me play devil's advocate. I think it can hit the x-axis. Mick, I think it can. Right? I think it can, So, prove to me that it can. Okay, let's start with my argument. Devil's advocate. I think it can. If it could hit the x-axis, what would y be?
0.
Y would be 0. That's the definition of the x-axis, correct? The definition of the x-axis is it hits 0. What you're about to understand is why your calculator farted out when we had that 8, 0 in there. So, if we assume that it can, then we go, okay, rule, we assume that it can. We'll play your stupid game. That means 0 equals 267 times 0.53 to the x. Yay! Good. Solve that for x with me, shall we? Let's solve for x. Let's solve for x. How would you start solving that for x? Lego. What would you do first? Lego method.
Get rid of the exponent.
Oh, I'll do that first, because that's not what happened Lego building. Lego building started with the 0.53, then applied, order of operations. 0.53 to the x, and then at the end, multiplied by 267.
You divide by 267.
So we have to get rid of 267 first by the Lego method. You got to get rid of 267. What's 0 divided by 267?
0.
0. You can divide 0 by anything as long as it's not 0. 0 equals Gesundheit. 0 does not equal Gesundheit. 0 equals 0.53 to the x power. Now here's where I don't want to bring up the word I said I wouldn't use more than once, and I already used it once, so I can't use it again.
Logarithm?
Yes, you said it, not me. So there's a mathematical tool that allows you to get rid of where that x is. But let's think about it a different way. Let's try some values of x. Let's just try some values of x. Give me a nice value of x that we can try. 1. X to the first power. If that's 1, what's 0.53 to the x? It's 0.53. Well, that's clearly not right because that's not equal to 0.
Yeah.
Yes. How about 0.53 to the 12th? I was going to go with squared.
It's all going to be wrong.
Why is it all going to be wrong? 2. Exactly. Why is it all going to be wrong, Carrie?
Because you're always going to have 0 equals another number.
Because the problem
It's
is,
never true.
yes, it's never truly 0. It'll keep getting smaller because as you keep increasing this guy, you keep multiplying a number less than 1 by itself. Make this 0.5 to make the math easy. 0.5 times 0.5 is 0.25. It got smaller. 0.5 times 0.5 times 0.5, that will be x cubed. That's 0.125. That's even smaller. 0.5 times 0.5 times 0.5 times 0.5, that's 0.0625. It's even smaller. 0.5 times 0.5 times 0.5 times 0.5 times 0.5, that's 0.03125. That's even smaller, and it keeps getting smaller. But what will it never be?
0.
It never can get to 0. That's because that graph you were just looking at is called asymptotic. It's a great word. Asymptotic. Wonderful. It's got 3 Greek 3 Greek words put together. Asymptote. To not fall in line with. Or to fall in line with. Check this out. Check this out. When you look at the graph of that, it keeps coming down and it's starting to flatten out, yeah? But flattening out is relative. Yeah, it's closer than it was back there, but it's still not touching. It's still not touching. That's why you can never ever be equal to 0, because this number is always positive, and this number is never positive. You can't have something positive equal something not positive. It's kind of how mathematics breaks when stuff like that starts happening. So that's why it's the perfect model. We're out of time, unfortunately. We got 4 minutes left. Not enough time to do it all. Cards we'll do on Monday. Do cards on Monday. But I also want you guys to understand how important these two numbers are with your data. Has anybody figured out the connection between these two numbers and your data yet? Sure. Really slick connection. It's not perfect. It's not perfect, but it's so damn close. So we'll come back down on Monday as well. There's a really, really neat connection between those numbers and your data, and we'll see something similar over here with you guys as well.
What if we drew x and 0?
X and 0 is fine. Because that's essentially before you guys flip, right? X0 makes this whole thing equal to 1, makes that equal to 267, which is damn close to 289,
Yeah, that's
which you guys started at. Oh! Yes, we'll come back to that. That was a lot in 30 seconds.
Yeah.
Yes, I agree. Don't think about it. Don't think about it. We'll play with it on Monday. Play more on Monday. It's good. Well, thank you. You do the same. Hi.
So I just wanted to see if you actually did this right.
This looks beautiful.
So
The average rate of change, the number of candidates decreased by 1 point. Is this in percentages? I forget what those are. Are they in percentages? Oh, 1.8 per 100,000 per year. That's the, if you think about it, this is why I think in the quiz I said you have to use the word per twice. So since the numbers in that chart, 215, it's 215 deaths per 100,000 men. So there aren't percentages here. Right, per year is what makes it per year. So it's down 1.8 deaths per 100,000 men per year.
Okay.
It's only because that's the way they gave me the numbers in the chart, was per 100,000 men.
Okay.
So that's like I said, 2 pers in there.
Okay. And so then this is the equation.
That's beautiful.
So I put in.
Beautiful, 31, you got 116.87, that's awesome. There should have been 170 deaths per 100,000 men, love it. You Googled the population of the United States, cut it in half, love that. You multiply all this out, you got what the hell? So, this is what I'm going to do. Yes, negative 40% essentially. You're off by 40%. It sucks. Why? You should have been. This is perfect. This is perfect. The reason?
Yeah.
What did you do when you did that year? 5 times a day. Did you? Boom. What's the danger of extrapolation?
Yeah, because,
Think of the bank housing one. You're guessing, you're basically guessing, and you're making an assumption that the behavior of the data is going to keep doing what it's doing. In other words, that data is going like this, yeah?
you're guessing.
Yes, but what happened was it went something like this. But we didn't expect that. So that's why you got to be careful extrapolating. That was the whole point of that. Was be careful extrapolating because you can get a meaningless number. Everything's perfect.
All right,
If you want to change that per, just submit it. Cool?
Just a question.
Yes.
I'm kind of an idiot because,
No, you're
well,
maybe you. No, you're not even.
E, F, and G.
Yes.
But I don't know why I didn't put them on
I
here.
don't know why you didn't either.
Because
I couldn't
did
find them
it
anywhere.
with green, and then it was on a different piece of paper.
But you didn't staple it in.
Yeah. So I don't know what to do.
Well, you can fix 5 points of it
Yeah.
with the rated A coupon and just say, duh, I forgot it. Or you can fix, well, that's good, but you got to look at the coupon. If the coupon tells you to do it, you have to print the coupon, resubmit, separate paper, sentences you have to write. Look at the coupon and see what the coupon tells you have to do.
But it's like 24 hours.
No, that's the project coupon.
Oh, but this
The
is.
project is if you forget to do a project. Look at all the coupons. There's a project, exam, and a quiz. This is the exam. So
Okay,
look at
and
the one
then how
there.
many quizzes do you have left to turn in?
Your progress report tells you.
Yeah, okay.
Whatever it says, it's a big
Yeah,
yellow
oh, no,
box.
no, I get that. So what I meant to say is,
How many more will there be?
Yeah.
At least 1 per week for the next couple weeks. Probably closer to 2 per week. So that's probably around 8. We're still recording. Hi.
2, 4.
What?